Okay, so this is actually a quick review from last unit. We're going to use it this unit. So we talked a little bit about last unit. So we talked about phase changes and like the energy of phases and so forth. So we're using it this unit because now we're talking about more along the lines of how are the phases heated and how much energy does it take to do so and so forth. So I'm trying to hit some more of the conceptual understanding because our last multiple choice from gases, that's pretty much what killed people's averages on that test. Your free response was beautiful. You had your units, your equations, you were pretty dang good on that. And I'll give it back to you after I finish a couple people taking the test. But the multiple choice was horrendous. Okay, so we need to focus on conceptual stuff first, and then we'll do calculations today. So I've got 2 videos that'll help with that too. Just trying to fill in the gaps that you guys are missing here. So from the perspective of a heat curve, you always start off with what? What is this? Solid. And then what happens to it? It melts. And then what happens? You go to liquid, and then what happens? It vaporizes or boils, and then it goes to gas. Okay. Is pressure involved in heating whatsoever? No. So phase diagrams, where you had phase diagrams, it was pressure versus temperature. These don't have pressure involved at all. So we're going to talk about temperature versus what? Time or what? Energy added. Energy added can be kinetic energy added, or it can be heat added. They phrase it in different ways. So we talked about the 3 different motions of energy. Three different energy motions yesterday. I'll say that. What were the 3 motions? Vibration. What's the definition of vibration? It was funny. Wiggling in place. So okay, vibration, and then translation, and then rotation. Which do you think is going to be the main motion of solid particles? Vibrations only. So we have simply vibrations here, good vibrations in the solid phase, and then what do you think is going to happen as we get to liquid phase? We'll have vibrations and translation or rotations, or maybe a little bit of both. That one's kind of hard to tell because they're flowing past each other, so they're definitely translating, but they could also be rotating. So that's going to be, I'm going to say plus translation. Okay? Just keep it simple. And then obviously gases, we have a lot of motion. We've got vibrations, rotations, and translations. So you can just see it's a slow build of every type of energy motion possible. Okay, so that helps us to see how solids start at low energy, gases go up to high energy. When we say energy, we're talking kinetic energy here. Now let's skip down to the intermolecular forces. Which of these states of matter has the highest magnitude of intermolecular forces? Solid phase, right? So the solid phase here has the strongest or highest IMFs. So as you start, you can see the solid phase is heating. You can see the temperature is rising. There is a delta T associated with that first slant. There's no delta T associated with the melting phase. Why? Okay, so the temperature is constant, but heat is added. So what's actually happening? What's the heat being used to do? Why do you think we just talked about this IMF thing? Breaking apart the what? Molecules, bonds, what? IMFs, the intermolecular forces. Okay, yeah. You're using it you're using the energy to cause the melting process to occur, which is simply taking solid particle and solid particle and separating them to a particle and a particle that are farther away from each other. So you're overcoming the IMFs in this phase here, and we called that last week melting or delta H of fusion. We wrote delta H fuzz. Remember that? That was the endothermic process of melting, okay? So this is going to come back to us today. And then our next phase is liquid phase. What could you tell me about the IMFs there? Getting further apart, so they're weaker, but I'm just going to say medium IMFs here. Okay, so then now replicate what you just said for fusion. Tell me what's happening here at the vaporization stage. Okay, not bonds necessarily, the molecular forces are broken. I don't like to say bonds because when you say bonds, I think ionic bonds and covalent bonds, and they are not absolutely not broken in phase changes. Just the interactions between them are overcome is the word we use. So you're overcoming the IMFs from liquid phase to gaseous phase, and then what would you say about the IMFs of the gaseous phase? Very low. What if we assumed ideal gas? None. I'm going ideal here. So then we would say no IMFs, period. So the reason that these heat must be applied for the melting phase and the vaporization phase is not because you're trying to change phase, it's because you're trying to overcome these IMFs. And the IMFs are, they're like magnets and you have to overcome them. So that's why the heat energy is required despite the fact that there's no temperature change, period. Okay, so we're going to use this heat curve today, so leave some space around it because we'll probably will add some information to it as we go. Let's do video first on heat energy transfer, and then we'll talk about endo and exo, and then we have some notes on problems. So we have all kinds of stuff to do today. Oh, this is my first one. Name off all the energy types you can. Kinetic energy. What else? Potential. Keep going. Kinetic, potential. What else? Any kind of energy. Heat, thermal energy. Thermal. Sound is a form of energy. Infrared. Waves like the sun, solar. UV energy, okay, which is from the sun. Gamma, okay. Radio. Micro. Microwaves, huh? Micro. Unit of metric. I feel good about myself. Okay, geothermal, hydro, you can go on and on, right? So we're really narrowing down our focus on thermal energy today, heat energy. And that's what our basically our unit topic is for this full unit, okay? Let's watch the video first and then we'll take down a couple notes. This video, write down 5 bullet points that you feel are concepts you should know. And I'll kind of jet in as we go, but 5 bullets of information. Why did I do that?
HP storage guy Calvin Zito, and I want to help you answer a question. Why does HP 3 parse?
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 47. It's on heat exchange. If I were to say, don't touch this iron right here in the middle, it's hot, what does that mean? Well, we know that it has a higher temperature, and therefore it has a higher amount of average kinetic energy. And if you were to touch it, a lot of that energy is going to be transferred to your hand, and that's going to produce quite a bit of pain. And so if we ever have a warmer body and a colder body, the warmer body is going to have more kinetic energy. And again, that energy is in the molecular motion of those molecules moving around. And we're going to have more energy in that than the colder body. And so a good way to represent that, and I'll use this model over the next few videos, is just using these little cubes that represent the amount of energy. In this case, that's going to be thermal energy. And so if I were to put those two objects in contact with one another, that energy is going to be transferred. In other words, energy is moving from that first object to that second object, and we call that transfer heat. And so what we're really doing is transferring energy as thermal energy or heat. Now heat, if you were to look up heat on the periodic table, you're simply not going to find it there because it's not a substance, it's not a thing, it's just the transfer of energy. And so a good way to think about that, and this should be a sentence that should kind of roll off your tongue, energy is being transferred as heat. That's real.
Okay, so energy is transferred as heat. That's the phrase we like to use when we're talking about thermodynamics and thermochemistry, which is our topic for the day. So energy is transferred as heat, meaning, we can talk about kinetic energy, we can talk about potential energy, we can talk about all these types of energy. But kinetic energy is what we're really focusing on because that average kinetic energy is what creates our temperature and our temperature of a system. So we like to, I need those as well today. I just need a couple. We'll take one and I'll get some. We'll do the lick and tear method.
Liar.
Okay, so let's finish this.
What's going on. And so when we're looking at energy being transferred as heat, it's going to vary depending on the substance that we're dealing with. In other words, metals are going to transfer energy through heat more readily than things like wood or brick. So let's look at this PHET simulation. So I've got iron, I've got brick, and then I've got water. And so we can assume that we have the same amount of each of these. And if I were to put the water on top of a heating device and the iron on top of a heating device, and I were to just increase the amount of energy, what I'm going to see is an increase in temperature. Well, what's really...
So you see the iron's increasing really fast, and the water, okay, he isn't heated yet, but it's going to heat really slow. So thinking about capacity, so specific capacity, which of these do you think has a higher heat capacity? Heat capacity's definition is the amount of heat required to raise the temperature of 1 degree of that substance by 1 degree Celsius. By 1 gram, sorry, 1 gram by 1 degree Celsius. So who's taking longer to heat? Water. So who has a higher heat capacity? Water. Okay, so do you go get in the ocean right now, based on the temperature of the ocean?
No.
No, because it's had a full 4 months of cold. It's gonna take a long time to get up to nice happy temperature for me to get in there. Now, but we'd all probably go to the ocean versus chemistry right now. Let's be real.
Going on is that we're speeding up those molecules. That's speeding up the molecules of the thermometer. It's spreading apart. Likewise, when we cool it down, what we're doing is we're cooling down those molecules, cooling down the molecules of the thermometer, and therefore it's going down. But we really don't see that energy transfer as heat. And so now what we're going to do is we're going to click on the energy symbols button, and now we're actually going to see that energy inside those molecules. Now as I'm heating it up, what's really happening is I'm adding energy. I'm adding energy to that iron. Now you can see that some of it is being transferred out to the environment through heat. Likewise, when I cool it down, what I'm doing is I'm actually transferring that energy as heat into the ice cubes. So they have lower kinetic energy. What happens if I take that iron and I just throw it into the water? You can see that since it's hotter, it's transferring some of that energy as heat as well to the surroundings until it eventually reaches what we call equilibrium. And so if you ever have a warmer and a colder body, that warmer body is going to have a higher amount of average kinetic energy. And remember the Maxwell-Boltzmann distribution shows us how that works. If we were to
Okay, how would you know, I know it's labeled as in the red, it's higher temperature. How would you know that the lower curve here is of higher temperature? Anybody got me from yesterday? Jason? Okay, I know it's hard to see on this one, but this red line probably stretches all over to his head. Okay, so the top range is of higher energy, meaning the top range can be indicative of the maximum temperatures they could endure. What else could you tell? There's 2 ways to tell. We talked about the range. The blue range is short, the red range is long. What else?
Fewer molecules.
Not the fewer. Don't worry about the fewer part. Instead of looking at the y-axis, look at the x-axis. Tell me what you're going to say, because I think you're on the right track. Go for it, Jack.
There's going to be more energy transfer.
They can have more energy transfer, but
It's getting more energy quicker.
so remember, an average kinetic energy is what temperature is representing, right? So the average of a curve is always the peak. The average of this curve is this peak. So this red peak is at a higher energy temperature than the blue peak, which is back over here. So you can look at the peak area where the energy lies, or you can look at the range of energies in which they can endure. So 2 ways to find that. That's called the Maxwell-Boltzmann curve.
look at it, this would be the cold body and this would be the warm body. Now in each of those bodies, they're going to have low energy particles and really high energy particles. But in the warmer body, that average kinetic energy is going to be greater. And so if we ever put them in contact with another, there's going to be a lot of collisions between these molecules. And as they collide, they're transferring some of that kinetic energy. And so what we're really doing is we're transferring energy from the warmer object to the colder object through heat until they eventually reach what we call thermal equilibrium. In other words, it's the same average kinetic energy on both sides. And that picture I showed you of iron at the beginning, eventually what's going to happen is all of that iron is going to have the same amount of kinetic energy because we've transferred that energy out. Now, it's not the same for every substance, and so we use a term called specific heat capacity to measure that. And so
write down specific heat capacity and write down his units and then our units. Generally, I really try to help you guys by keeping Kelvin in gases. Kelvin, anytime I say Kelvin temperature, we're really talking about gases. In the real world, we can use Kelvin like anytime, any place. But in thermochemistry, which we're in right now, I try to talk about Celsius all the time. So he has specific heat denoted as joules per gram degrees Kelvin. What we're going to talk about is joules per gram degrees Celsius, but it's essentially the same thing. It's just a temperature unit. So gold, aluminum, and water. We obviously see water has the highest specific heat. Who's going to take the shortest to heat up? Gold. Good. Gold, because it has a really, really low specific heat. Metals are all going to be like under 1, like 0.1, 0.2, 0.9, something like that. Usually they're under 1, most of them. Water has a super high specific heat.
right here you can imagine we have a kilogram of gold, a kilogram of aluminum, and a kilogram of water. And let's say that they're all in a container. And so if you look at it, they're going to have different amounts of specific heat capacity. If we look at the units, that's joules, which is a way that we measure energy, per gram. and then Kelvin or degree Kelvin. And so if you have something that has low specific heat capacity, that means it's going to be changed, the amount of energy it has is going to change more readily than something that has a higher specific heat capacity. So let's add a little bit of heat to this and watch what happens to the thermometers. And so the gold, the aluminum, are heating up more readily than the water. Now the energy is going to be the same, it's just that the water has a higher specific heat capacity, and so it's able to absorb more energy before it starts to change its temperature. And so did you...
He just said the energy is the same, so that means Q energy is the same, but what was different about all three? The heat capacity and the temperature change, right? So Q might be the same, the C, which is specific heat capacity, and delta T can be different. It's okay. Heat and temperature are not the same thing whatsoever. So that's what we're going to see now. Yeah.
So, is electric conductivity proportional in a way to capacity?
Electrical conductivity, no, because that's more about resistance, like what's resistance? Ohms. Thank you. So it's more about resistance, about the conductivity of it, and like how loose the electrons are. Not necessarily about heat capacity. The energies are two different energy types, so they're not really good. I mean, they might. They're good. Okay, so basically, heat we will call the sum of total energy. Temperature we'll call the average. Please do not write down every word here. You've seen a lot of this before. Q is the sum of the total kinetic energy. T or delta T, depending upon like if we're talking about a change in temperature or not, will be the average kinetic energy. Actually, no, not delta. Sorry, just temperature. So that's basically what that video is supposed to help with, showing how, you can have these different variables, how they're related, but how they're not the same. Because a lot of times people say, oh, energy increase, so temperature increase. Well, maybe, but let's see. So one more intro video up here today. Thumbs up when you got this. Okay, do not write this down. Okay, I just want to talk a little bit about this. This is more conceptual stuff. Basically, we know we're dealing with chemistry. We're not dealing with electricity. We're not dealing with like geothermal stuff. We're talking about reactions. So a lot of times we talk about reactions as reactants versus products, right? And you always have bonds involved. You have ionic bonds and you have covalent bonds. So where really is a chemical reaction getting its heat from? Where's it getting its energy from? It's coming from the bonds. Bonds are a fantastic way to store energy. So to break a bond, okay? So give me a bond, Jalen, like this. Okay, to break this bond, I'm gonna have to karate chop her. Okay, I'm gonna have to like put some energy into this. That would be an endothermic reaction to break that bond. Okay, that's how I can get energy to be associated with bonds. But bonds forming actually releases energy. So it's all about the bonds in chemistry. So what they're trying to do right now for the big energy crisis we live in every day, they're trying to find a way to store energy in chemical bonds. So what they're trying to do is form lots and lots and lots of hydrogen gas, store it underground, and then use like ways that you can break the hydrogen bonds to get the energy back. So you can store it in hydrogen bonds, like H2, not like interlink the forces hydrogen bonds, really easily. So for chemistry, we're always talking about the bonds. And then we always talk about energy can flow between two systems, not necessarily through chemical reactions, but we talk about energy flowing a lot. So you just want to get used to these two phrases that we'll learn. Don't worry about the last one. Okay, let's do this one, and then we'll do actual notes. So this one, we talked about endo and exothermic reactions already. These are going to have graphs with them. So last week, we talked about like reactions, and if energy was put in, it was endo. If energy was put out, it was exo. But now we want to see how the graphs are represented. So be ready to draw a graph or two on this one.
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 33. It's on endothermic and exothermic reactions. If you understand that therm means heat and exo means to exit or to move out, it's pretty easy to break down these reactions. So an exothermic reaction would be one where heat is being released from the reaction. So a thermite reaction right here, you can almost feel how hot that is a reaction where we're releasing energy, releasing heat from the reaction itself. And likewise, if we have an endothermic reaction, that's going to be one where the reaction is taking in heat. And so in a cold pack like this, there's a combination of water and ammonium nitrate. That reaction is consuming heat, it's taking it from the surrounding, and so it's going to feel cold over time. And so you really have to understand what is the system and what are the surroundings. And so in a reaction, the system is going to be where the reaction is taking place, so in the chemicals themselves, and then the surrounding is going to be outside of that. So if we have a change in heat, that's either going to be an exothermic or an endothermic reaction. Now in the lab, we can't really see at the level of the atoms, and so we have to view it macroscopically. And we do that by simply measuring the temperature change. And so in an exothermic reaction, we're going to find that heat is being released from that reaction to the surroundings, and in an endothermic, it's actually being absorbed.
Okay, let's draw this as a picture. We have two types of reactions, endo and exo, but we're considering something called system and surroundings. That's something you would have defined in your reading guide 17. So I'm going to leave this here and here. Okie dokie. So basically, you have a system, and that's usually where our reactions are happening, some sort of chemical reaction, right? You have something around the system. What do you think it's called? The surroundings, right? So there's like there's a physical barrier between them. Like this might be a chemical reaction that's happening, and then around it, there's a cup, or there's water, or there's a container. They're just two physically different things. So the system versus the surroundings are what we always talk about. But if the law of conservation of matter, of energy occurs, the energy that's lost by system A will go to surroundings, or that's lost by surroundings will go to system. You cannot destroy energy. It's always conserved. So if this reaction is putting out energy, putting it out, or giving energy away to the surroundings, what would you label that as? Endo or exo? Exo, because we chemists, we focus on the system. The surroundings is a real person too. We have to care about it, but we're focusing on the system. The system is losing energy. It's an exothermic reaction. So what would happen if you put a thermometer in this? Let's call this as water. Let's say this is water out here, okay? If you put a thermometer in here, what would happen to the thermometer if energy is going out? Temperature would go up. Good. Temperature would go up. All right. So then what if you had a system that was cold, we'll say, and the surroundings were warm? Or what if we had a system that required energy to get started, so energy was going to go into the system? What would you say? Endothermic reaction. Where is it getting the energy from? The surroundings. So what's happening to the temperature of the surroundings?
Decreasing.
They're dropping. Good. Okay, so these thermometers are going to be useful for us to read the temperature changes, because we obviously can't see the energy particles scooching through the system and surroundings. So this is what he's talking about. Exothermic, increasing temperature. Endothermic, the system gets more energy, but the surroundings that you're measuring are decreasing in temperature.
Now, a really neat way to observe this is to use a model, is to use a energy diagram like this. And so the way it works is that the energy progress will be going along the x-axis, and then the amount of energy in the reactants and products is going to be displayed. And so in an exothermic reaction, what you'll see is a downhill reaction. In other words, the reactants are going to have more energy than the products. Now, where is that energy going? Where is that heat going? It's going to the surroundings. And likewise, in an endothermic reaction, the reactants are actually going to have less energy than the products, and so they're consuming that energy. And so let me give you an example of that. Here's that exothermic reaction again. We've got a thermite reaction where we're taking iron oxide and aluminum, and we're making iron and aluminum oxide. Now, this is a really intense reaction, and it provides the oxygen in this form of combustion. And so this should be able to work even underwater. But if we were to look at
Where has this reaction been used before? Do you remember Breaking Bad when they broke into breaking into whatever the manufacturing was, they used thermite.
Energy diagram of this over time, as it progresses, we'd find that these reactants, the iron oxide and the aluminum, have a higher energy. In other words, there's more energy locked in those bonds than we're going to have in the products. And so we can see this as a downhill reaction. Now, what's going on? Why do we see this increase in energy here? Remember, we have to start pressuring those bonds, put a little bit of pressure on it before we can actually have them break apart, and we get that exothermic reaction. And we call that a activation energy. So you're going to put a little bit of energy into the system, but you can see that we're going to net energy coming out of that. And so that's going to be measured in heat coming off that thermite reaction.
Okay, so what he just drew was an exo or endothermic reaction. He drew an exo. So he had energy here, and we had reactants going up to products, right? So overall, reactants going to products, there's a decline in energy. So where did it go? It exited to the surroundings. Good. So what you would label here is from the energy of the reactants to the energy of the products, there's a difference. That difference is called delta H. So is that delta H a positive number or a negative number based on the fact that you know it's exothermic? It's negative, right? It's going down. It's a negative number. He also mentioned one more thing, and this is the part that he didn't draw, but I'll draw for you. So this is the energy differences between the products and reactants. That's called delta H. The energy that it takes to kind of get the reaction started, that he said you got to pressure the reactants into actually reacting. You have to give them a little ump. You gotta add some energy. And the energy is the difference between the reactant energy up to the tippy top of the hill. So basically, the reactants have to put forth this amount of energy. This amount of energy is called EA. Activation energy. We talked about this a little bit a couple weeks ago. It's literally the energy of activation required to activate the reaction. Got that? Okay, what was your question? I had two questions. Yeah.
So, I hear about that scene where goes into where
he steals methylamine. Yeah. The precursor to meth. Okay. So do the same thing on his graph for the next one he's drawing, which is endo.
Now, if we look at an endothermic reaction, again, this would be like solid ammonium nitrate, and we're just combining it with water, so we're going to make ammonium and nitrate ions. In that case, what we're doing is the reactants are actually going to have a lower amount of energy than the products. And so you can see here's our activation energy, but this is an uphill reaction. In other words, it requires energy, it requires heat. Where is it getting that heat? It's getting it from the surroundings. And so when we're measuring ectothermic or exothermic and endothermic reactions in the lab, we're really stuck with the temperature itself.
Sorry, I didn't give you guys a chance. Did you guys see his graph? Looks like, which one did he just draw? Endo? That. You got that? Notice the hump again. So between exothermic and endothermic, which has a higher activation energy? Endothermic has a humongous, right? Look at this activation energy. From reactant energy to tippy top. Huge energy that must be put forth. That's a lot of activation energy. And in this case, you can see the delta H value as the difference between the reactant value and the product value. Well, that value is about yay big. Okay? And endo is positive or negative? Positive, because it's requiring energy to be put forth into it. So those are different types of graphs. And these are called reaction coordinates. It's just showing how the reaction is coordinated. It's going through this process. So we'll use these throughout the year, but I want to introduce them now because they're definitely relevant right now, okay? So now we're going to talk more about Huckel's MCAT stuff we introduced yesterday. So this is kind of like a broad scheme conceptual stuff. And I mean, I'm going through this time to do this. I'm really hoping that this was beneficial. If you didn't write anything down, I'll see that in your portfolio check. So we just did that. Okay, so we're going to, I think a lot of you guys will help you a lot in terms of remembering the formulas. So I'm going to do this early this time, day one. So come get a piece of paper, and if you grab a piece of paper, great. If you want a piece of paper, what color is your choice? You can share scissors with a buddy, that'd be great. Okay, your foldable will be folded in with 4 flaps, and I'll show you how to do that in just a second. Oh, we're going to pass these out. Basically like this. You can fold it in half, and then each of the panels in half again. So fold it in half first. And you have to work through the half is full half again. I have a bigger piece of paper than you, but it's okay. We need 4 doors. Just fold it in half. And then fold each of those halves in half. Then you go to scissors and you cut yourself some windows. I mean, doesn't have to be exactly this. I'm just trying to get you guys, you know, an easy way to fold just the half, and you fold each half in half. And then cut here. You're creative. You can do it. So if you need a buddy, they'll help you. No, you're good. That's basically what you have. You just have longer paper. I just have longer paper. I was like, yeah. It's, guys, fold it however you want, whatever your heart desires. It will be fine. After you get your flaps cut, these are the labels put on the outside. The labels are up here on the board, not on the outside. No, I don't think we can line. I just have this from you. Do you mind being black and white? Hold this up. Hold it up so I can see. That's what I want. All of it. For the barn doors. And label the outsides of your barn doors. Here, 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 here. You can do some pencil, marker, whatever, but this is kind of interactive notes so that you guys can have a foldable, have some notes, have some example problems all at the same time. I don't know if you, I haven't scrolled down yet. I will ask for effective use of color at the very end. Effective use of color. Happy face. But this is what we're going to be doing. So start by labeling your flaps as here, as I have here. Label your flaps like I have on the board. Oh, you hate them. Does everybody have a paper I pass back? Yeah, Miss Emma. Okay, thanks, guys. Okay. Oh, actually, does anyone have a back side, Vinny? That was my next question. Does it have a back? Okay. Look on the paper I just passed back to you. I have the foldable instructions for you printed out. You see them? Yes? Okay. Put a star by that, because that's what I have on the board as well. So you don't have to, take picture or anything. It's not online. It's right here. Extras, I'll get it. Okay. So today we're going to talk about all of these. I would say 3 and 4 flaps at least. We'll do thermochemical equations tomorrow. But we're going to talk about all of these. And within each of them, I'm going to give you notes. And your notes can go in your foldable or they can go on paper. But I'm having you do the foldable now, so it's more as like, you have one complete set of information. All the equations, all the information and where, like what kinds of problems you use the equations, the units, and an example, like a picture that would help visualize what the process is. So I'm trying to hit some more concepts for you guys since we struggled on that for gases. So I'm going to talk about each of these today. So leave yourself some space on the inside of the flaps. You got the outside of the flaps labeled? Yes, yes? All right, moving on then. So this is for you for reference, but you have a copy of it. You label the outside of your flaps. We're rolling. All right, first flap is the Q equals MCAT line. This is a scenario in which you would use this. The scenario is right here in purple. Write down the scenario.
I like the picture more as MC Delta Hammer.
Delta Hammer?
MC Hammer.
Oh, MC Hammer then. That'll have to be a convention we'll come up. We'll have to develop that. That'll happen every night. All right, so this is the scenario because you'll see the first bullet point says description of the type of problem or scenarios when this formula should be used or what should be happening in the problem. So what's happening in a type of problem that you would implement the formula Q equals MCAT is when it's talking about internal heat internal heat of something, or when heat is, you're calculating heat, but the heat does not say it's transferred with anything. So like this might just be a piece of metal. Just a piece of metal. Not metal with metal, not metal with water, not metal with hand, not coffee with hand, not coffee with mouth. There's no, system and surroundings, just the system that we're talking about. So does that make sense about the scenario? You're given like one identity of a substance. Yeah. Doesn't matter to me. I just want to give you a general sense, and you guys can go with that. Okay. So each of these variables involved has a meaning, has a unit. So let's write down the variables involved in the units. What is Q representing? Heat. What is heat measured in? Joules or calories. But very rarely will we see calories. So we'll see one example today. I'm gonna put like a scratch through it or put rare or something next to that because I really want you to know that heat's in joules. I mean, it could be in kilojoules, but joules, okay? What's M gonna stand for? We talked about this yesterday. Thank you. Mass. What do you think mass is measured in? Grams. What is delta T? I'm sorry, I just skipped something. What is C measured in, or what is C representing? Specific heat capacity. We just watched a video on that. Good. Specific heat capacity. So what do you think the C is coming from? Capacity. Okay. That has a bigger unit, right? What was it from the video?
It was like 0.1.
That's the number. What was the big honking unit? It was like a fractional unit. Gram degree C. Good. So we're going to use this degree Celsius because I'm trying to keep gases as Kelvin stuff, thermo as Celsius stuff, so you don't get them mixed up. And then delta T. This was on our warm-up sheet from yesterday. Delta T was change in temperature, which was T final, so temperature final minus temperature initial. And what is that measured in? Degrees Celsius. So we have now killed two birds here. Definitions of the variables used, including units. So the diagram, here we go. There you go. That's it. Told you it's not like nothing crazy. There wasn't heat transfer between two things. It's literally the heat of a specific substance, like a metal or just water, something like that. So that one doesn't really have a picture for it. But what we would do is I would give you 3 of these variables and you would find the 4th one. So if you know how to define your variables, you're in good shape. All right, so now that's the easy one. The next one is Q is equal to Q. So it's our second flag. And I put on the board a negative Q and a positive Q, and I'll tell you why in a second. But write down the scenario right here in purple for Q equals Q. And I can scroll back up if needed. The second flag, writing down the scenario right there in purple. It didn't really matter where you put it. It's got to go with the Q and Q1. Bring them a couple. Okay, so whenever you have a system and a surrounding, that means that they're going to be allowed to have heat transfer between the two. So one of them is going to lose heat while the other one gains heat, right? You can't lose heat and lose heat because you have to have a conservation of energy. That's a big joke, right? So I laugh every time I see, I think I saw this on my computer, but I didn't see this. On the light switch it says, turn off the lights, conserve energy. Joke's on you, energy's always conserved. Doesn't matter if they're on or off. Only smart people get that one. Okay. So we have information about conservation of energy. Energy is transferred between the substance and surroundings. And a lab setup we always use with this is called calorimetry. So this is like an experiment that you would set up, and you're going to talking and writing. This is a lab that you will actually be setting up tomorrow. It's called a calorimeter, a calorimetry experiment. So whenever we calculate heat, calculating heat, like joules, is really, really hard. Or sorry, measuring joules is really hard. Calculating it is easy, because I can literally measure the mass of something, I know the specific heat of something, I can measure the delta T, and I can calculate joules, but I can't really measure joules. So what I have here is a couple of scenarios. A lot of times you'll have one system, one thing that is losing energy and the other one that is gaining it. So the sign is simply showing you which is losing it and which is gaining it. So if I say I have a rock, put it in some water, the rock is hot, the rock warms up the water, what's happening to the rock? Is it losing energy or gaining energy? Losing it. So negative Q of rock, because it's losing energy, is equal to positive Q of water, because the water I said heated up, so it gained energy. So you just have to label it so you know what the heck you're talking about. Now, since I can't usually find Q that easily, I like to use what Q is equal to, which is Q is equal to MCAT, right? So I like to say MCAT of the system, aka rock, is equal to MCAT of the surroundings or water. So we use MCAT in this one, but they're set equal to one another. So the sign is just simply showing you the flow. Now, how does this setup work? We will have tomorrow a little coffee cup calorimeter. It's literally a styrofoam cup, because styrofoam cups are really, really good insulators. We're going to put water in it tomorrow. The water will be considered our surroundings. We're going to drop something really hot in there. We're going to drop it like it's hot as well. So this is going to be your metal. Your metal is going to be just really, really hot. And the metal dropped in the water, what do you think that metal is going to do to the water? It's going to heat it up. So the system would be considered the metal, the surroundings would be considered the water. You can measure some stuff and determine heat exchanged or delta T, or you can determine any of these variables. How many variables are involved here? Different. So this is for the rock. This is for water. So we have 6, right? 6 different data points I could give you. I'm going to give you 5. You find the last one. Okay? Those are a little harder. There's just a lot of data, really. Okay, the last one we're talking about for now is this one right here. Q equals moles times delta H fuzz. I have delta H fuzz here. It could have been delta H fusion or vaporization, condensation, sublimation. I could give you any phase change, but it's just delta H's phase change. So the scenario is when a phase change is happening, when you have no delta T. This is the delta H one. So you wrote down moles times delta H. So tell me, if I don't give you delta T, what equation can you absolutely not use? If I don't give you delta T, you can't use MCAT. So you can't use MCAT, you can't use MCAT equals MCAT, so you really have no choice. Like, you cannot get this wrong. You have to use one equation like this. Q, or heat, is equal to moles. I could also give you mass, because you can convert mass to moles, right? You're powerful in all ways. And I can give you a value for delta H diffusion, or I can ask, given that, ask for Q, I can ask you 2 different ways. So during a phase change on the plateau, remember the plateau over the heat curve? Right here? These are the phase changes. I can ask for the heat exchange, which is overcoming the IMFs. So the way you could do it is Q is equal to moles times delta H. The delta H must be in units of, and I'm going to erase it right here. It must be in units of kilojoules per mole. What cancels? In this example, what cancels? Moles. So what's the energy left? Kilojoules. So it's an energy unit, so Q is expressed in kilojoules many times in equations like this, and that's fine. But on you have a reference sheet that you guys will have access to soon. The reference sheet has stuff expressed in joules per gram. I generally don't use that one, so you won't see me often use it, but you can use it yourself. So if I ever give you Q, I could also if I ask for Q, I could also see you using mass times delta H, but expressed in joules per gram. So if mass is in grams, then what cancels here?
Mass.
Mass, right? So the mass and grams cancels, so you get joules. You get joules again. So there's two different varieties of this one. For water, we'll generally be doing this for water. For water, the values you need to know, and I'm going to tell you them now, so I don't have to tell you later. Delta H of fusion of water. Ready? Fusion of water means what? Fusion is the special word for melting. Good. Okay, so fusion of water, the energy required to melt ice is 6.01 kilojoules per mole. 6.01 kilojoules per mole. And the energy required to vaporize water, which means vaporize, boil, right, is 40.65 kilojoules per mole. Those are two standard values, and I would always give them to you. If I don't, just ask. Yeah. The second one is a boiling water. Vaporizing is boiling. All right, let's talk about specific heat a little bit more, and then we'll do some practice problems. Yay! We're almost done. You guys are going to practice a lot today. And if you don't know the specific heat definition yet, it's right there again. But that's for you. Okay, I will come back here if needed. Oh, you want to see this one? Here we go. What did I do? Ice to liquid. There you go. Phase change. No delta T. Something like that. You can get crazy with it. Or you can draw yourself a little heat diagram here, a heat curve with the circle phase diagrams. Whatever floats your boat. Okay, so I'm going forward. I do have these two values you need to write down as well. Sorry. Write down those for the water specific heat capacity. Water is going to be probably 90-95% of our problems. You're going to want to know these, okay? So write these down someplace for yourself. The C for water is either 4.18, you can do 4.186, whatever floats your boat, joules per gram degree C, or 1 calorie per gram degree C. We will be using that value quite a bit. Fun fact, it is higher than any other substance, really. Metals, I told you, we're going to be about what for specific heat? Under 1, like 0.5, 0.6, 0.9, whatever. Water is 4.18. That's crazy high, okay? So we'll use that a lot. You can't see this chart at all, but I have some examples of different metals, gold and copper and so forth.
Not like rubber.
That's not a specific, no, it is a specific substance. It could be a blend, though. I don't know that one. You could look it up probably. You can find a specific heat for pretty much everything. It melts pretty. Oh my gosh, I don't know. It is heat. On the recycled labels, it's got like 1, 2, 3. It's like high density and low density. They're what's the word for this? It's from your guys' project. Thermoplastics. You can heat them and they'll melt. The plasticizers help them become plastic. I can remember it later. Okay, so look on the back of your page where it says Unit 6-ish, Question 1. You see those lecture problems? Yeah? Notice I printed problem set 17 for you, because anytime we have extra class, any extra class time, you will be doing problem set 17. You guys wait until the last minute to do problem set 14 and ask me a million questions, and I wasn't here. So we're starting early. All right, so this is the first one on the lecture notes, and you guys will be finishing these today. First one, let's do this one together. We'll do one from each subset. Identify your variables, write your givens, choose the formula. You guys find it? Okay, so identify variables, let's go. Read it and tell me what I should be writing. Whenever you get your paper out and stuff. Read this question, which is number 1 under lecture practice. And tell me what I should be writing.
1.55.
Okay, what variable is that? You're right, but what variable? Mass, thank you. Mass is 1.55 grams. You have to identify it because, just writing 1.55 grams is not going to scream to me the formula I use, right? So make sure you're ready. So a piece of stainless steel weighing 1.55 grams absorbs 141 joules of heat. What does that mean? Q is positive, it's endothermic, so it's absorbing. So positive 141 joules. Keep going. Next piece of information is, right, because it says it's increased by, so it's not telling me where I start at or where I end at, so I don't have a T final and a T initial, but I have the overall change, which is easier. So delta T is 178 degrees C. Question. What am I looking for? Looking for C. Okay, so if you write it down like that, you cannot get this wrong. What equation? Right, Q equals MCAT. MC delta T is just harder to say, so we say MCAT. All right, so what variable am I isolating? How do I do that? So math, divide by math, okay? There you go. All right, so then C is isolated. Specific heat, and I'm only going to walk through like how to isolate variables very rarely now. We are algebra 1 and 2 proficient, hopefully, or whatever they're called, math 1, 2, 2.5, I don't know where you guys are. Okay, so Q is 141 joules over what? 1.55 grams and degrees Celsius. Okay, so what are our units going to be in the end? Joules over grams degrees Celsius. Is that the unit of C? Yes. Okay. So calculate. Do that for me. We're going to practice calculating in class because some of us still cannot put that in our calculator correctly. The denominators are just so tricky. Calculate. Tricky, tricky. First one, tell me he's right now.
First one.
0.511.
No, it's not.
Yes, it is.
It's
Don't mess with me.
0.5112.
Oh, but she was doing sig figs. You never told me. Yeah, okay, good. All right, so you guys are good here. Q equals MCAT's pretty easy. There's very limited variables that will be given. All right, smile big and toothy when you're ready. Big and toothy. Thank you. I see very few smiles. Thank you. Okay. You guys just toothy right here. All right, now, this is the next set of questions. You have calorimetry now. What equation did you use for calorimetry? Yeah, and?
Moles per...
No, calorimetry. Q equals Q. Okay, Q the surroundings equals Q's in the system, which does have MCAT in it, right? But MCAT equals MCAT. So we have 6 things we're looking for. Now, that's a lot of data. And I have done this since I was 15. When do you take chemistry? Yeah, 15. So I've been doing this forever. Trust me, it works. So please try to progress with me on the data. So as you read through, I'm just going to peruse this for a second. What is the specific heat of 50 grams of a metal that raises 100 mils of water? So we have 2 identities, water and a metal, and a calorimeter, blah, 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 blah. Okay, so we already know we have 2 things we're dealing with. So I'm going to make a little table here, metal and water. And I can already see, looking at the information, I'm given M, I'm given T's, and I know my C of water already, so I like to make myself a chart like this. And if you're an organizational person, you're going to be all over this. All right. So what, as I go through, tell me where I'm filling in the boxes. What is the specific heat? What is that? That's my question, yeah? Where's my question mark going? C of metal, thank you. 50 grams of metal, mass, good. So 50 grams of metal. That raises 100 mils of water. What is that? Huh? It's a volume, but volume's not here, right? So it must be something else. 100 grams, thank you. What's the density of water? 1 gram per 1 milliliter. Generally, we don't measure water out like on a scale, right? We measure it in the volumetric, not volumetric flask, a graduate cylinder. So that's our mass of water, 100 grams. Okay, so it raises the water in a calorimeter from 34 to 36. 4 for water, right? Okay, because they're different. We have 2 delta T's. So I'm just going to write it out. I know you can do this in your head, but 36 is T final, 34 is T initial. Subtracting that gives us 2 degrees C. Oops. 2 degrees C. All right, so that's our delta T of water. The initial temperature of the metal was 95. The final temperature of the water and the metal was 36. What can I find from that? The metal was? Okay, so the metal was 95, so that's Ti, right? This is, it is now 36. So 36 is T final minus 95, which is T initial. So T final minus T initial is what for metal? How much? Negative 59 degrees Celsius. You will always have one increasing in temperature and one decreasing in temperature. It's okay to have a negative. Don't be scared. Okay, we're missing one more thing that we already know. What is it? 4.186 joules per gram degree C. Okay, so we're literally looking for C of the metal. So to show your work for this, once you get the hang of it, you can minimize your work as much as you can. But for the first couple, you need to kind of get the hang of it. So the rule is Q equals Q. Q of metal equals Q of water. Q is negative. Who's losing energy? Metal. So it gets the negative, the Q of the water is positive. Now, Q's are worthless. We don't have anything about Q here. We have MCAT stuff here. So I'm going to rewrite this as negative MCAT of metal equals positive MCAT of water. Just helping me isolate my variables to make sure I plug in right. You don't know how many people put N is equal to RT over PV on PV goes on RT stuff. You trying to do it in your head. If you can't do it in your head, just do it on paper. Who cares? Take the extra 5 seconds. Isolate C for me. Which C are we isolating? So what am I dividing by? Negative mat of metal. Okay, so divided by negative mat of metal. So the negatives cancel here, the M's cancel here, the delta T's cancel here. We are stuck with C of metal. Yay! And we are plugging in this big honkin' fraction. All right, so as long as you labeled it water and metal, you cannot get it confused. You can if you really try, but don't try. Get it right. What's the M for the first one? For the numerator? Huh? 100 grams of water. Okay. Keep going. C is water. 4.186 joules per gram degree C. Delta T? 2 degrees C. Okay, so everything so far was about water. So you plug all your values in, divided by the negative sign that's associated with this. What's the mass? 50. So 50 grams of metal and negative 59. If you don't put the negative there, your negatives won't cancel. Your negatives will always cancel, okay? You cannot have a negative mass, right? You can't have a negative C value. That's just a standard positive value. You can have a negative delta T if I ever asked you for delta T, but generally your negatives will cancel. So when you plug this in your calculator, how much you get? Anybody? One more? Units? Okay. We just need to get that to sig figs. I think this was like 59.0 and 2.0, so 2 sig figs? 0.28. Okay, so basically you should have seen everything cancels except for the specific heat, specific heat capacity. Grams and grams cancel, degree C and degree C cancel, and so you're left with joules per gram degree C, which is the specific heat unit. So we're in good shape here. Does that number make sense for a middle? Yeah, it's below 1. We're doing pretty good here. So you can always reflect on your answer at the end. Now, if you were one that you were like, oh my gosh, this is way too much work, then if you give this, if you can isolate the data in your head and plug straight in, I'm okay with that. I'm just trying to set you up for success here by giving you data nice and organized, plugging in nice and organized. Or you could calculate this as Q, because that's Q for water, equals or over this. You know, you can modify it once you get your basic understanding. Okay, so that's our calorimetry type. Make a note on number 2 for me. Number 2, I gave you the C in what? Calories. So the block of rhenium metal has a C of blah, blah, blah calories per gram degree C. So what C would I be using for water? Would I be using the joules one? No, because it doesn't cancel. 1 calorie per gram degree C. So that's the C for water for that one. Just, you know, I'm just showing you one that does have calories in it. I'm not going to give this example that you can do that one. Okay, let's do the big boy. We have the phase change one. I have 2 examples I'm doing there because I have a really, really easy version and a really kind of not as easy version. Oh no. Forgot to erase the slide. Close your eyes.
Wait, what did you say? The homework was 1 through 9.
I'm going to have to modify that because you guys are, you always have more time in this class than you do. Okay, so looking at this one, we have the heat of phase change. Which equation are you using? You already know. What equation are you using? Q equals H times moles or molar mass. Okay. So we'll probably have molar mass involved here someplace. Okay. So I'm going to go ahead and write down Q equals moles times delta H because that is what we already know is phase change heat one. But let's read. So question is how many grams of water? So question grams of water at 100 degrees C and 101.3 kilopascals. Have we talked about pressure at all in this unit? No. Okay. This is a conventional way to describe a reaction. We don't really care about what temperature it's happening at necessarily, or the pressure at which it's occurring. We don't care because we just want to be able to do the problem. But conventionally, they give you this information. Cross it out. It's a distractor. This is like you go to the restaurant and they pretty much, do they ask you if you want ice in your drink? Probably not. They just give you ice. They don't ask because you don't really care. You're like, yeah, I'll take it. So it's a similar, okay, just a conventional way to write. So the question is, how many grams of water at blah, 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 blah could be vaporized? Why is the vaporized important? HVAP. So this gives us now the phase change that we are concerned about, vaporization. After the addition of 180 kilojoules of heat. What is that? Heat. Q. You have to know Q is heat. Okay, so knowing this information, what do we not have? We don't have grams, but what do we not have from the equation? No, we do have delta H. What was it for water? I just told you it.
40.65
Thank you. Kilojoules per mole. Okay, so I've given you this value already. So what do we not have in the equation? Moles. If I can get you to moles, can you get to grams? Totally. You're awesome people. Okay, so using this equation, I'm isolating what? Moles. So I'm dividing by what? Delta H. Thank you. You're dividing by delta H VAP. You're dividing by delta H VAP. So moles is equal to Q over delta H VAP. What's Q? What's the value for Q? 180 kilojoules. And what's the unit, or what's the value for HVAP for water? 40.56 kilojoules per mole. What cancels? Kilojoules. Where's the mole go? What happens to the denominator of the denominator?
Goes to the top.
Goes to the top from your little floppy dot shop stuff. So your moles, it was like 4 point something. 4.4. 6, give me one more. 37. Okay, I didn't think it was 4. Okay. So 4.37 moles of water is what you got. Last step. Convert to grams. What's the molar mass of water?
18 something.
18,016. Thank you. 4.37 times 1 mole, 16 grams of water is like grams of water. There you go. Oh, dang it. Right there. I didn't erase that earlier. Okay. I'll scroll up a little bit. Now, I had a heat curve here because you might have to use a heat curve. In this one, did we see anything about like temperature changes from maybe like 0 degrees Celsius to 100 degrees Celsius? Did we go through anything but a phase change here? We went through vaporization, that was it, right? We didn't go through like heating stuff and then vaporization, we were just simply vaporizing. So this was an easy phase change one. I'm gonna go forward. Is that okay? Yeah. Okay. Now I'm gonna give you one. It's number 4 on yours. Number 4. Oh, I didn't. Give me a second. Sorry, resetting between first and second period is sometimes a hassle. So read number 4 on yours for me. You're reading it?
How much heat is required to change 2.9 grams of ice at negative 15 degrees Celsius into steam at 230 degrees Celsius?
Holy cow, we're going from ice to steam, right? How many phase changes are we undergoing? 2. Don't forget the heat curve has a phase change here and a phase change here. But isn't the temperature changing here, here, and here? Yeah? You have the power now to calculate Q of temperature changes, here, here, and here. And you have the power to calculate Q of phase changes, here and here. How many Qs are we talking about? How many different areas of the heat curve are there here? 5. 1, 2, 3, 4, 5. Okay? We are going to have to account for every single change that happens to this poor little ice that we're heating up. And it's going to come in different ways. Okay? So sometimes there's a delta T involved. We use what equation? Delta T is involved. We use what equation? MCAT. If delta T is not involved, AK, during a phase change, what equation do you use? The moles delta H thing, right? So we're going to do this 5 times, okay? So we're going to go through the logistics of it, and we'll see if we go ahead and calculate. But it's good for you to draw a heat curve, draw yourself a heat curve, and let's label this baby. You got a heat curve drawn? I'm just giving you your tools to get you started, okay? And I'll let you guys do this by yourself. So your heat curve, what's your starting temperature? According to the problem. Negative 15. So this ice down here is at negative 15 degrees C. And it goes all the way up to what top temperature? 230. Okay, so there's a lot of delta T's going on here. But as the ice melts here, as the ice is going from 15, it's going to go up to a specific temperature, but it's still an ice phase. It's just changing temperature. It's slowly heating up. What temperature does it start to melt? 0. Okay? So what is the delta T with the first segment? 15. So 0 minus a minus 15, or negative 15. So delta T down here is 15 degrees C. Okay? Then it's going to be going through this phase change here. There's no delta T, so what equation are you using here? Q is equal to moles times what? Of fusion, because that's what melting is fusion. So delta H fuzz. Oh, I didn't write the Q in here. This one down here says that there is a delta T associated. What equation are we using to find Q for this small segment? Q equals MCAT. Okay, so Q1 is the first lamp. That's MCAT. Q2 is the phase change at melting. Q3 is going up to what temperature? Right, 100, because you have to, thanks Levi, I was trying to figure that was, because you know that that's where water starts to boil, so the liquid's going to top out 100. What is the delta T here? 100, good, because you're going from 0 to 100, so it's just a 100 delta T.
Real quick.
Huh?
Real quick.
You scared me. So this is Q3 is equal to what? What equation? MCAT again. Okay, and then we have, what's happening now? Vaporization. So we have a Q4, which can be accounted for by what equation? Moles times what? HVAP, because that's the vaporization one. And then finally, we do what? We get from what to what? So what's the delta T here? 130, because you're going from 100 to 230. That difference is 130 degrees. And the equation you would use here? MCAT. So Q5 is equal to MCAT. Okay. So this one's a lot of work. Okay, I'm not gonna lie. This one takes five different equations, or 5 equations. They're not really all different. The values that you need to be aware of are, we already know one of them. What is the C for liquid water? 4.18. Sorry, I'm trying to write C liquid. C liquid water is 4.186 joules per gram degree C. Every state of matter of water has a different C. And I would always give these to you. I can't even remember these guys. Specific heat of ice. So the C down here for ice is 2.05 joules per gram degree C. And then for steam is gaseous water is 202 joules per gram degree C. So now you have those values for yourself. If the question asked, what is the total energy required to cause this ice from -1 or -15 degrees C to go all the way up to 230? After you get all these babies, what are you going to do with them? Add them up, okay? So at the end of this big adventure, you're going to add all your Q's, and that will be total energy used, right? There was one caveat here. What was the unit that I gave you for fusion and vaporization?
40.56 or something.
Kilojoules there, right? Kilojoules per mole? So I gave you kilojoules per mole there. These Q's down here, the Q goes MCAT, Q goes MCAT all the way, those are all going to be in joules because that's what the C value is in. So just be wary. At the end, either convert 2 joules or 2 kilojoules and then add them. Okay? Take 5 minutes and finish that problem. And then you guys can start on the rest of them. Yeah. Yes. Thank you. Finish that one, and then I will adjust. Let me see what I can do for homework. I'll leave it at this. 1 through 9 on your lecture notes. We already did number 1, right? We already did. There's 2, 3, and 4 in the first one you still need to do. We just did number 1 for the calorimetry. You're going to do all the way through 5 there. And you're finishing this one. Okay? The rest of those under the heat phase change, you can finish those tomorrow. Okay? I would also say to start from set 17, like at least the true false stuff, you want to inch your way through that. So notice that we have, tomorrow we'll finish up notes, we'll do specific heat lab. Thursday we'll finish up the last bit of the foldable, which is that last section. And we have another lab. And then Friday we have 30 minutes of review. Because I'm 75% done teaching this week, okay? And then we have a quest, okay? So after that, we'll be done with heat. Heat's like a 5.5 unit, so it's like a mini unit. So thank you very much for your time. You have 15 minutes left to practice. Ask away.